we'll first discuss the inclusion-exclusion formula for 3 sets and its applications, and then we'll move on and we'll talk about probability theory. So, but first, exclusion formula for 3 sets. So let A, B, and C be all sets, and we would like to find the formula giving the number of elements in the union of all 3. So we're after the number of elements in A union B union C. And we can get started with just the sum of elements in A, in B, and in C, which would be the correct formula if there are no pairwise overlaps between A and B, B and C, and A and C, right? Then the sum rule would apply for 3 sets, and this formula would be correct. But in general, what we have is the following. I'm going to depict this on a Venn diagram. Let this be A, B, and C. So if you apply this naive formula to this situation, then you'll find that some elements will be single counted, and those are the elements which are only in A and not in B and not in C, only in B and not in A, not in C, and only in C and not in A or B. And others will be double counted, those which belong to the double intersections, but not to the triple intersections, right? So these elements here will be double counted, double counted, double counted, and in a triple intersection, those elements will be present both in this number of elements in A, in the second one, and in the third one, so they will be counted 3 times instead of just once. Okay, so we need to introduce corrections to ensure that all elements are counted precisely once. And the first idea is that, well, let's correct first the elements which were counted twice by subtracting numbers of elements in the pairwise intersections. So let's try this formula. Number of elements in A plus number of elements in B plus number of elements in C minus number of elements in A intersection B minus number of elements in A intersection C and number of elements in B intersection C. So let's see how that works. Well, for those elements which were double counted, those now become counted precisely once. So those elements which were in a double intersection but not in a triple one. So they would be present, for example, in terms in A intersection B but not in C. Those would be present once in this number, once in the number of elements in B, and only once in A intersection B, but since they're not in C, they wouldn't be present in the second correction term, and they wouldn't be present in the third correction term. So those are now singly counted. And same goes for the elements which are in the other double intersections, but not in the triple intersection. So what happens now at the very center, where we have the triple intersection? So in this formula, these elements come with a plus 3 times, because they will be present in the first term, in the second, and in the third term. And they also will be present in each of the negative terms. So now they're not counted at all. So we have 0. They're not counted because they're counted with a plus 3 times and with a minus 3 times as well. So we need to introduce one more correction, which concerns only those elements. And it's really easy to bring them back in just by adding with a plus the number of elements in the triple intersection, A intersection B intersection C. Okay, so you can put there 1 again to signify that they're counted exactly once, and this is what we have derived, called the inclusion-exclusion formula for 3 sets. Well, it's called inclusion-exclusion because you see there are alternating signs here, so you need to exclude certain sets, and then you need to include certain ones again. Right? And a version of this formula also exists for 4 sets, 5 sets, etc., and it always has the same structure. It has alternating signs, so you start by adding the numbers of elements in each set together, then you subtract numbers of elements in double intersections, then you bring back in triple intersections, then you subtract quadruple intersections and so on. But the good news is that we will only practice with the formula for 2 sets and for 3 sets, right? So we don't need to memorize all of those other formulas, but I just want you to know that those generalizations exist for arbitrary number of sets. Okay, let's see how this formula can be applied to counting problems. So I'll start with the following example. So it will contain some data. So it's known that a total of 200 students took a course in Scottish Gaelic. So 200 students took a course in Scottish Gaelic. 150 students took a course in Irish. 60 a course in Welsh. Furthermore, it is known that 30 students took both Irish and Welsh. And 90 took both Scottish Gaelic and Irish. Scottish Gaelic and Irish. And 20 took both Scottish Gaelic and Welsh. And 3 students took all 3 courses. How many students have taken at least one of these 3 language courses? How many students took at least one of these 3 courses? Question mark. Okay, so this is sort of some data is given about the students. So first we need to formalize these and introduce the 3 sets, right, with which we will be working. And we'll introduce some notation. So let capital S stand for the set of all students who took the Scottish Gaelic course. All students who took the Scottish Gaelic course. Let denote by capital I the set of all students who took the Irish course. Who took the course in Irish. And by W, let's denote all students who took the course in Welsh. Okay, once we have introduced these 3 sets, we can convert all the data given in terms of numbers of elements in these sets and their intersections. So let's do that. In terms of these three sets, the number of elements in S is given to be 200. The number of elements in I is 150. The number of elements in W is 60. And then what comes are the numbers of elements in the double intersections of these sets. So 30 students took Irish and Welsh, so I intersection W, number of elements is equal to 30. S intersection I is equal to 90. And Scottish and Welsh, so S intersection W equals 20, contains 20 elements. And the number of elements in the triple intersection is I intersection S intersection W, that's given to be 3. All right, what next? So we converted all the data into these numbers of elements and sets. What about the question? So students who took at least one of these three courses, those would belong to the union of the three sets. Right? So we are after the number of elements in the union. Okay, so we want to find I union W union S. So using this general boxed formula for the three sets, we can write this as the number of elements in I plus the number of elements in W plus the number of elements in S minus all the double intersections. I intersection W, I intersection S minus W intersection S plus the triple intersection I intersection W intersection S. And finally, substituting the numbers, we get 30 plus 90 plus 20. Sorry, no, those come with the minus signs. Sorry, wrong ones. So the 200 plus 150 plus 60 minus 30 minus 90 minus 20 and plus 3. And this finally gives us the answer of 273. Okay, so here was really a straightforward application of this formula. I really wanted to illustrate these steps. When you introduce the sets, you convert the data into information about numbers of elements in various intersections, and you convert the question also to finding the number of elements in a certain set. Any questions about this? This is first example. Okay, and let's do something more interesting, which involves sort of a more creative use of this formula. Okay, so let's look at the following example. So among first-year computer science students, all have to study at least one of the three languages: Python, Java, and C++. Maybe this is gated. Won't it? Yeah, some people laugh. Among first-year CS students, all have to study. CS students in 1995 all have to study at least one of the three languages: Python, Java, and C++. So then comes some data. There are 106 first-year CS students. There are 106 first-year CS students, out of which 50 study Python, 60 study Java, and 30 study C++. Okay, more data. 13 students took both Java and Python. 14 took both Java and C++. 12 took both Python and C++. Two questions. Find the number of students who took all three courses, all three languages. Find the number of students who took all three languages. And question B, find the number of students who studied both Java and Python, but not C++. Who studied both Java and Python, but not C++. Okay, so that's the problem. And I will first introduce three sets, right, which correspond to three subjects, three computer languages. So let P stand for all students who took Python. So P for Python, J for all students who took Java, and C for C++. Okay. Next step, I'll convert all the data given into some information about these sets. Okay, so what we have? Number of elements in P, that's given to be 50. 60 students took Java, and 30 students took C++. And then come double intersections, Java and Python, 13. Java and C++, 14. And Python and C, 12. And there is one more piece of data. So one has to look carefully and make sure each number is now represented as a statement in terms of the sets. So one more number is given is 106, and that's the number of first-year CS students. Moreover, we're told that among first-year students, all have to take at least one of the three languages. That's a requirement. So that means that this number 106 actually gives you the number of elements in the union of all three sets, right? So that's probably less trivial in this data, but if you combine the condition that at least one of these courses must be taken, and altogether there are 106 students, then we get that the J intersection P intersection C is equal to 106. Okay? So, in part A, what are we asked to find? Find the number of students who took all three languages. So we are after P intersection J intersection C. Okay. So we're going to use the inclusion-exclusion formula, but this time around we will know what stands on the left-hand side, the number of elements in the union, and on the right-hand side we will know all the terms except for the last one, the triple intersection. So we will have to rearrange the terms to find this number of students in the triple intersection. Okay, so by the inclusion, exclusion formula, so the number of elements in the union, P union J union C equals the sums of the numbers of elements in each set minus the double intersections P intersection J minus J intersection C minus P intersection C plus P intersection J intersection C. Okay, now we substitute the numbers. So 106 must stand on the left-hand side. On the right-hand side we get 50 plus 60 plus 30 minus the double intersections which are given, minus 13, minus 14, minus 12, and plus what we are after, P intersection J intersection C. So moving all numbers into the left-hand side, we get P intersection J intersection C equals 106 minus 50 minus 60 minus 30 plus 13 plus 14 plus 12, and that gives us 5. Okay. So that's the answer to part A. So let's look at the second question. Find the number of students who studied both Java and Python but not C++. How can we write that? So they must be in the intersection of J and P, right, but not in C. That means we should take the set theoretic difference, right? We should remove all the elements which would be also in C, and we're after the number of elements in this set. So, well, it doesn't look immediately like something which would involve this formula for 3 sets, right? Because we don't have such constructions. So we either have double intersection, triple intersections, or triple union, right? So we don't have intersection minus something. Well, we could use actually the complement. If we agree that the union of all 3 is our universal set, then not in C we can write as belonging to C bar, right? Everything outside C. So we can write this as a triple intersection. And this might suggest to use the inclusion-exclusion formula for the sets J, P, and C bar instead of C. Right? But then it would involve lots of quantities which are not directly given to us in the data we know. And so if there may be a possible route like this, but actually it turns out to be rather complicated. If you continue pursuing it, that you quickly find that you don't have the data needed to extract this from the inclusion-exclusion formula. If you're at a loss what to do, my general advice is draw a Venn diagram. And life may be, in fact, a lot less complicated than it seems to be, right? And you can see what's going on in the Venn diagram much better. Let's do that. So let's draw Venn diagram. So let this be C, P, and J. So we are after the students who took both Java and P, so they're in the double intersection of J with P, but we should exclude those who took also Python. after the number of elements in this shaded set, right? And we do know that, well, in this triple intersection, we calculated in part A that there are 5 students who took all 3, Java, Python, and C. And also, we know that in the double intersection, we were given from the start the number of elements in J intersection P is 13. 13, right? In the whole thing. So we know that the number of elements in the shaded area should be 13 minus 5. Right? So it just follows from the picture when you identify what you know in it, right? Then here comes the solution. And we can write it like this. So J intersection P minus C, number of elements here equals the number of elements in J intersection P minus the number of elements in the triple intersection. And substituting the numbers, that gives us 13 minus 5, which is equal to 8. Okay. So the moral of this example is don't try to mechanically use just given formulas, right? But instead, you can draw a Venn diagram and see much clearer, you know, what you know and what you have to find. Any questions about this second example, please? Generalize to what? To the example, this particular example. Yeah, of course, something is always true. If you have a double intersection, yeah, so this is true for arbitrary 3 sets, J, P, and C. You know, this first part, right? It's always the number of elements in the double intersection minus the number of elements in the triple intersection. That formula is certainly always true, but rather than, no, I'm urging you to just remember to draw Venn diagram and figure things out on the spot rather than memorize more formulas. Right? It's not very economic. More questions, please? Okay, let's then move on to probability. Okay, just a second. Let me rearrange things here. So, you know, yeah, in this course we have many different topics, and they can seem to be very different, but you know, they all are interconnected. And in particular, combinatorics, or methods of counting, is very closely related to discrete probability theory, right? Because essentially, to calculate probabilities, you calculate various configurations, right? So these two topics are linked together, and today I just want to introduce the main ingredients in probability theory. So very briefly, probability theory provides mathematical models for understanding uncertain situations, and such uncertain situations are called random experiments. Here are some examples. For example, when you flip a coin, that's a random experiment. You roll a die, or you draw a lottery ticket, or you bet on the outcome of some football game. So these are all examples of uncertain situations. A couple of examples from computer science. When you design a software, you don't know what input data will be used in it. But you might be interested in understanding how efficient your program will be in processing this data. So you can treat the input data as some random experiment, right? And then you would like to find, say, the average time or maximal time it will take to process the input of a certain size. So probability theory actually is quite important for designing reliable software. Another example is, say, a random number function which is present in any computing programming language. For example, in C++, that's a runC function that returns a random number. So in reality, this is mimicked by certain very complicated formula, which takes as a seed, for example, today's date, and it's put into a certain function, which is called a pseudo-random number generator, and it's supposed to really, I mean, for it to work, you need to check that this function really will produce outcomes which look random. So it's another example of when probability is important in computing. So the mathematical probability model has two main ingredients. The first one is the sample space, and the second is the probability function. And the sample space, which we will be usually denoting by capital S, is the set of all possible outcomes of the experiment. Here are some examples of sample spaces. If you flip a coin once, then you have only two possible outcomes, heads or tails. So your sample space S contains two elements, and you can denote them with letter H for heads and letter T for tails. If you flip a coin twice, then you have four possible outcomes, which correspond to heads or tails obtained one after another. So you have four ordered pairs of elements from the first set, so that's H and TT. That's the Cartesian product, actually, we introduced when we talked about set theory. If you roll a die once, then the possible outcomes are integers from 1 to 6. So the sample space contains 6 integers corresponding to 6 possible outcomes. In some situations, you have actually infinite number of elements. Consider the following experiment. Flip a coin repeatedly until you obtain a head. Right, so that's your experiment. These are the prescriptions for flipping a coin. And therefore, you have the following situations. Either you obtain heads at the first flip, then it corresponds to just H, and you stop. Or at first flip you obtain tails, but then at the second flip you obtain heads. So it's TH, that's the second possible point, possible outcome in this experiment, and so on. TTH, TTTH, and so on. And here you're not told, when to quit and give up. You're supposed to, in this idealized situation, supposed to do it as long as necessary. So there will be elements in this set which correspond to any number of attempts which yielded tails before you obtain heads. So you have infinitely many elements in this sample space. In this first four examples, sample spaces, they're what is called discrete sets. They have finitely many elements in the first three sample spaces, and the fourth one, it's infinite, but the elements are countable. You can count, this is the first element, second element, third, and so on. In such situations, when you either when you have finitely many elements, or you can count your elements, we say that we have discrete set or discrete sample space. And in some situations that's not enough. Real numbers comes in. For example, if you want to measure lifetime of a bulb and you do it repeatedly for many bulbs produced, then the lifetime can be an arbitrary real number, right? In this case, the sample space is the set of all positive real numbers. And these real numbers represent the hours of lifetime. So this is a continuum sample space here. So in this course, we'll be mostly focusing, well, pretty much we will do only the situations with finitely many points in the sample space. But probability theory, in principle, goes beyond and tells you how to handle the other situations as well. Okay. So some more terminology. Any subset of a sample space is called an event. It's just probability theory terminology. So here are some examples of events. So let's consider the experiment in which a coin is flipped 3 times. Then the total sample space will contain 8 elements listed here, right? So it will be all possible combinations involving H and T for heads and tails, so strings of 3 symbols. And you can count that there are 8 of them, so you can just count them as they are written out, or you can use the rules of combinatorics. You have 2 choices for the first outcome, for the first flip, 2 choices for the second flip, and 2 choices for the third flip. So the total number of possible outcomes is 2 times 2 times 2, which gives you 8. And this easily generalizes to more flips. And so in this situation, we consider an event, let's call it A, which tells us that heads came out twice. So this singles out the subspace A, representing this event, which contains all outcomes satisfying this condition. Heads came out twice. So it could be HHT or HTH or THH, because it's not specified in what order they were obtained. So it gives you 3 different points. So it's a subset containing three elements. Another example, a game of football is played, and we can describe it by, say, sample space which contains pairs of non-negative integers, which correspond to the number of times the first team scored and the number of times the second team scored. And then we can consider an event A, which corresponds to having a draw. So here, in this sample space, it gives us a subset. I call it A1 here, which consists of all pairs of non-negative integers n and m, which are equal. So a draw means the number of times scored was the same, and this contains all of these pairs of equal numbers. It's a subset in the set of all possible pairs. One can also take here a simpler description with a different sample space called S2 here, where we don't record the number of times which were scored, but just say W for the first team winning, D for the first team losing, L for the first team losing, and D for the draw. Then the same event in this description corresponds to just one point D, one point subset D, which is a subspace of the sample space.
Why is flipping a coin repeatedly not continuous?
Because I can count all the outcomes. It's a known theorem that you cannot count all real numbers. So there's no one-to-one assignment. So this is the first real number, that's the second, that's the third. It's a theorem, right? You have to actually demonstrate that that's the case. But in that case, it's easy to see that you can count all the elements, just say by the number of attempts. So 1 attempt, 2 attempts, 3 attempts, 4. So they're countable. So they're not, they're not real. I mean, it's a subset of all real numbers, in some sense. Looks more like natural numbers, right? So you can make a one-to-one correspondence with a set of natural numbers with that. That's not as real. Okay. So events. The second ingredient of a probability model is called the probability function. So it assigns a value between 0 and 1 to any event, that is, to any subset of the sample space. And the intuitive meaning of that number, it indicates how likely it is that the outcome of the random experiment will be some element in that event. And so we will study just probability models which are postulated. So in this course, we're not addressing the issue of how do you choose the correct probability model which will describe some real substitution in real life. That's more of a problem for statistics, right? Testing hypothesis, right? You think of maybe this probability function is the right one and this sample space is the right one, maybe not. And there are, it's known how to check, how to test this. But we're not going to address that. I will only mention that in practice you can think that these probabilities are approximated by relative frequencies of the outcomes. And here in this table, I recorded some outcomes of flipping a single coin. And so you can record the total number of flips in the left column, the number of heads in the second column, and number of tails in the third column, so that they add up to the total number of trials, of course. And then you can record the proportion of heads, right? And although, so this is just one possible experiment, but you can test that you should assign probabilities for heads to be 1/2 and for tails to be 1/2 in a single flip by repeating these experiments many, many times and noticing that the proportion of heads approaches the number 1/2. So it may look like this: 0.7 for 10 flips, 0.46 for 100 flips, 0.494 for 500 flips. It's just one hypothetical situation. In practice, you never know exactly how fast the relative frequencies will be approaching the probabilities. It's a hard question. But I'm only mentioning this for you to know, to appreciate that there is this, there are difficult problems in establishing this interface between probability models and the real world. I'm not going to talk about this anymore. Instead, we'll focus on using concrete probability models to calculate probabilities. Okay. So, in probability theory, it's assumed that probability functions, they must satisfy 3 axioms, right? 3 rules. Well, the first rule just says what I said already, that the probability function assigns values to all subsets. So it's a function from the set of all subsets to the set of numbers, real numbers between 0 and 1. Okay? And the second axiom says that the empty set has probability 0. Something always happens, right? Empty set means nothing happened at all. And the probability of the entire sample space is equal to 1. Right? Because we assume that all possible outcomes are in the sample space. Right? So whatever happened, it will be a point in S, so the probability for the entire S is 1. And the third axiom is the most important one. It says that for any two disjoint subsets, or any two disjoint events, which means subsets, call them A and B, which do not overlap, A intersection B is empty, the probability of the union equals to the sum of the probabilities. That's the most important rule in probability theory. And this third axiom can be actually extended to an arbitrary number of events. So if you have n events, call them E1, E2, and so on, E sub n. We can look, if they are mutually exclusive, which means that all pairwise intersections are empty, then the probability of the union of all of them equals just to the sum of the probabilities of these individual events. So these axioms, they were formulated in 1930s, so last century. Before that, actually, people, for many, many years, people tried to develop probability theory because they were mainly interested in gambling. But there was no clear thinking of how to assign probabilities. There are various rules in the game, and some of them were not consistent. I will discuss these axioms first, and then I will actually show you how you can apply this seemingly very formal machinery to calculate probabilities, which people in the past could not calculate correctly. Probably on the next lecture, but that's my goal. So bear with me. I'll have to develop the formalism further, and then I'll do very concrete examples. So having that rule, if you have a discrete, or even better, finite sample space, then you know that each subset consists of elements. You can think of them as points in the sample space. And these elements are disjoint. So you can always represent any subset as the union of one element subsets, which will be disjoint. Which means that it suffices to assign probabilities to each element, to each point in the sample space, and then you can calculate probabilities of arbitrary events. For example, if the event E consists of certain points, E1, E2, and so on, E sub m, then the total probability is the probability of the first element, by which we mean, of course, the one element subset, plus the probability of the second element, and so on. Just sum them up. So to summarize, say slightly differently, if you want to specify a probability function, it suffices to specify its values on single elements, which could be just some negative numbers, and they all must add up to 1, right? So that to satisfy the second axiom, which says that the probability of the entire sample space is 1. If you sum up probabilities for each point, you get the probability of the entire sample space, and that must equal to 1. Okay, so that's the condition for specifying a valid probability function. And the most important model for us will be the equiprobable model. So it assigns to every point the same probability. So if you have a sample space with n elements in it, we can assign to every point from the sample space, to every element, the probability of 1 over n. Then the sum of all probabilities for individual elements will be 1 over n times the number of individual elements. So n cancels and you get 1 as required. And if you have an event, which is a subset from a sample space, then its probability can be calculated just by counting the number of elements in that event and dividing by the total number of elements in the sample space. For example, if your experiment consists in rolling a die once, then we have 6 points in the sample space, and we, in the equiprobable model, we assign probability of 1/6 to each point in the sample space. And then say if your event consists of all outcomes for which 3 or 4 occurred, that involves 2 points, 3 and 4, then your probability is 2 divided by 6, right? The number of elements in your subset, in your event, divided by the total number of elements. So total 6 is 1/3. Another example for rolling 2 dice, we have a sample space which consists of pairs of outcomes. Each outcome is again a number from an integer from 1 to 6. And we have 36 points in total. And say, for example, if we want to calculate the probability that a double occurred, right, we find all points which are included in the subset, which are points like 1, 1, that's it, 1 double, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. So there are 6 points there. Therefore, the probability for that event is 6 divided by 36, or 1 out of 6. And I stop here, and I will continue on the next lecture with problems.